What if the thoughts you repeat every day are quietly rewire the structure of your brain? Not someday in the distant future, not only after years of effort, but tonight, while you're listening, while you're resting. Most of us were taught, directly or indirectly, that the brain becomes fixed with age, that our habits, reactions, and ways of thinking harden over time like setting cement. But that story is incomplete. The brain is not cement. It is living tissue, responsive, adaptive, continuously remodeling itself through a process known as neuroplasticity. In this video, you'll begin to understand what that truly means, not just as a scientific term, but as something personal. You'll see how neuroplasticity allows experience to rewire your brain in subtle, measurable ways, and how small, repeated shifts in attention can increase neuroplasticity over time. No dramatic reinvention required, just steady, biological change. So let your breathing slow. Because inside your head, billions of neurons are adjusting their connections, strengthening certain pathways, softening others, reorganizing in response to what you practice and what you release. Your brain is not a finished object, it is a living system. And tonight, we gently explore how it changes. Neuroplasticity is the brain's ability to reorganize itself by forming new neural connections throughout life. Think of it this way. Imagine a vast forest stretching in every direction as far as your mind can wander. Now imagine that the paths through this forest are not fixed, they are not carved in stone or paved with anything permanent. Instead, they are soft dirt trails shaped by the footsteps of every creature that walks them. The more a path is traveled, the wider and clearer it becomes. And when a path is forgotten, when no one walks it for a long, long time, the forest slowly, gently reclaims it. Grass grows over it, wildflowers fill the space. The trail fades back into the earth from which it came. This is what neuroplasticity means. Your brain is that forest. Every thought you think, every memory you hold, every skill you learn is a path being walked into existence, and the forest never stops growing, it never stops shifting. It is alive with possibility, every single moment of every single day, reshaping itself with a patience and a grace that asks nothing of you in return. The word neuroplasticity comes from two smaller words, neuron meaning nerve cell and plastic meaning moldable or changeable. There is something almost tender about that if you sit with it for a moment. We do not often think of the word plastic in its original sense. We think of hard, shiny surfaces and manufactured things. But the root of the word is much older and much softer than that. It comes from the Greek word plastikos, which means to mold, to shape, to give form to something with your hands. Like a potter sitting quietly at a wheel, pressing wet clay into the curve of a bowl. The brain, then, is not a machine. It is not a computer, no matter how many times that comparison is made. It is something far more like clay, warm, responsive, yielding. It is shaped by what touches it, by what you experience, by what you pay attention to, by what you love. And the most remarkable thing is that you are both the clay and the hands. You are the thing being shaped, and you are also the one doing the shaping, whether you know it or not. That is the quiet promise hidden inside that small, beautiful word. The concept of neuroplasticity challenges the old scientific belief that the adult brain was fixed and unchangeable after childhood. For a very long time, for most of the history of modern science, in fact, the human brain was thought of as something that finished growing and then simply stayed the way it was. Like a house that is built and then lived in, but never renovated. Scientists believed that once you reached a certain age, your brain was complete. The walls were up, the rooms were set, and if something was damaged, if a wall crumbled or a window cracked, there was no fixing it. The house would simply have to stand as it was, broken and all. This belief held firm for over a century. It was taught in medical schools and printed in textbooks and accepted as truth by nearly everyone. And then, quietly, gently, the way dawn arrives before anyone notices, it began to change. Researchers started finding evidence that the brain was not a finished house at all. It was more like a garden that never stops growing, never stops sending out new roots and new shoots no matter the season. And with that discovery, everything we thought we knew about the mind began to soften and open, like a flower turning toward the light. Santiago Ramón y Cajal, the father of modern neuroscience, was among the first to suggest that the brain could change structurally. He was a quiet man, a Spanish scientist who lived in the late 1800s, and he spent his life peering through a microscope at the delicate, branching shapes of neurons. He drew them by hand in exquisite detail, the way an artist might draw the branches of a tree in winter, every fork, every taper, every curve captured with devotion. And through those drawings, through those long hours of silent observation, he began to suspect something that almost no one else believed. He suspected that the brain was not static, that it could change, that the connections between neurons could strengthen or weaken depending on how they were used. He did not have the tools to prove it fully in his time. The technology had not yet caught up with his intuition, but the seed was planted. And like all seeds planted with care and patience, it waited in the dark soil of science until the conditions were right for it to grow. Cajal gave us the first whisper of what the world would later come to call neuroplasticity, and for that whisper, neuroscience owes him everything. The term neuroplasticity was first used by Polish neuroscientist Jerzy Konarski in 1948. It is a strange and lovely thing, the way a single word can change the course of understanding. Before Konarski gave this phenomenon a name, the idea floated in the air like a melody without lyrics, present, felt, but difficult to hold on to or share. Scientists had observed hints of the brain's flexibility for decades, but without a word to contain it, the concept remained scattered across journals and laboratories, belonging to no one in particular. And then Konarski, working quietly in Warsaw in the years following the Second World War, offered the world a word: neuroplasticity. It was simple, it was clear, and it gave scientists a way to talk about something they had only been able to gesture toward before. A name has that kind of power. It draws a circle around an idea and says, this is real, this exists, this matters. And though it would take many more decades before the scientific community fully embraced what the word described, Konarski's contribution was the gentle act of naming, of saying aloud what the brain had been doing in silence all along. Neuroplasticity occurs at multiple levels, from individual synapses to entire brain regions. Imagine standing at the edge of a river and watching the water move. Up close, you can see individual droplets catching the light, spinning in tiny eddies, each one following its own small path. But if you step back, if you climb the hill and look down at the river from above, you see something else entirely. You see the whole current. The wide, sweeping movement of water across the land, carving valleys, shaping stone, finding its way to the sea. Neuroplasticity works in much the same way. At the smallest level, it is happening between two neurons, a single connection growing stronger or fading away, like a whispered conversation between old friends. But at the largest level, entire regions of the brain can shift their purpose, reorganize their function, take on new roles they were never originally designed for. The same force that reshapes a single synapse can reshape an entire landscape of thought. It is one phenomenon, but it moves through the brain the way wind moves through a field of grass, touching everything from the smallest blade to the widest horizon, all at once. There are two main types of neuroplasticity: structural plasticity, which involves physical changes in the brain's architecture, and functional plasticity, which is the brain's ability to shift functions from damaged areas to healthy ones. Think of structural plasticity as the slow, quiet work of a gardener. It is the growing of new branches, the thickening of roots, the careful building of something you can almost touch. When you practice a skill over and over, when you play a chord on a guitar or trace the letters of a new alphabet, your brain is physically growing new connections, strengthening the pathways that carry that knowledge. The architecture changes. The shape of the garden shifts. Functional plasticity, on the other hand, is something more like a river finding a new way around a fallen tree. When part of the brain is damaged through injury or illness, the remaining healthy tissue can sometimes learn to take over the lost function. It is the brain's way of saying, the old road is closed, but I will find another. And it does, quietly, persistently, with a patience that borders on devotion. The brain reroutes itself and carries on. Every time you learn something new, your brain begins to change, first through rapid shifts in electrical and chemical signaling, and over time through physical structural changes that are strengthened by repetition and sleep. There is something deeply comforting about this if you let yourself sit with it. It means that nothing you experience is wasted. Every book you read, every conversation you have, every quiet moment of observation sends a ripple through the living tissue of your mind. At first, the change is invisible, a flicker of electricity, a small pulse of chemistry between two cells. It is as brief and delicate as a firefly lighting up in the dark. But if you return to that experience, if you practice, if you repeat, if you give your brain the gift of time and rest, something deeper begins to happen. The temporary signal becomes a permanent structure. A new branch grows, a new connection solidifies, and your brain, the brain you will carry with you into tomorrow, is now ever so slightly different from the one you had yesterday. Not because anything dramatic happened, but because you lived, because you paid attention, because you let the world in, and your brain, in its quiet wisdom, chose to remember. Neuroplasticity is not a single mechanism, but an umbrella term for many different processes of neural adaptation. This is important to understand, and it is also rather beautiful. When we say neuroplasticity, we are not pointing to one thing. We are pointing to a whole symphony of processes, each one distinct, each one playing its own part, and all of them working together in ways that science is still learning to hear. There is the strengthening of existing connections, and there is the building of entirely new ones. There is the pruning away of pathways that are no longer needed, and there is the birth of brand new neurons in certain special regions of the brain. There is the shifting of function from one area to another, and there is the quiet chemical dance that allows a synapse to become more or less sensitive to a signal. All of these are neuroplasticity. All of these are happening inside you right now, layered on top of one another like the instruments in an orchestra, each one contributing something essential to the whole. And the conductor of this orchestra, the one who decides which instruments play louder and which ones rest, is, in many ways, the life you choose to live. The brain contains approximately 86 billion neurons, each capable of forming thousands of connections. 86 billion. Let that number rest in your mind for a moment, the way a stone rests at the bottom of a still pond. It is a number so large that it resists imagination. If you were to count to 86 billion, one number per second, it would take you more than 2,700 years. And each one of those 86 billion neurons is not alone. Each one reaches out to thousands of others, forming a web of connections so vast and so intricate that the total number of possible neural pathways in a single human brain exceeds the number of stars in the known universe. You carry this inside you, right now. Behind the gentle darkness of your closed eyes, a cosmos of connection is humming along. Quiet, faithful, unimaginably complex. And the most tender part of all is that this cosmos is not fixed. It is not frozen. Every one of those billions of cells is capable of reaching out to form a new connection or letting go of an old one in response to the life you are living. The universe inside your head is just as alive and just as full of possibility as the one above it. The total number of synaptic connections in the human brain is estimated at roughly 100 trillion. 100 trillion. That is a 1 followed by 14 zeros. A number so enormous that it slips through the fingers of understanding the way water slips through sand. To put it gently into perspective, if each synaptic connection were a single grain of sand, you would have enough to fill not just a beach, but an entire coastline stretching for thousands of miles. And yet all of it, every last grain, every last connection, fits inside the small, quiet space of your skull. It weighs about 3 pounds. It is soft to the touch. And within it, 100 trillion tiny bridges of communication are carrying whispers of thought, sensation, memory, and feeling from one neuron to another, every second of every day and every night. Even now, as you lie still, as your breathing slows and the world outside grows quiet, this vast network is at work, sorting, strengthening, softening, reshaping itself with a care and a precision that no human engineer could ever replicate. You do not need to direct it. You do not need to understand it. You only need to rest and let it do what it has always done, hold you together gently from the inside out. Neuroplasticity means your brain today is not the same brain you had a year ago. It has been quietly reshaping itself all along. This is perhaps the most personal of all the truths we will visit tonight. The brain you are using to listen to these words is not the same brain that woke up with you this morning. It is not the same brain that carried you through last winter or sat with you on a summer afternoon years ago. It has changed. It has been changing all along, with every experience, every emotion, every dream. The connections that were strong a year ago may have softened. The pathways that barely existed have grown into highways. Memories have been consolidated, skills have been refined, and somewhere in the quiet folds of your cortex, the person you are becoming has already begun to take shape. You did not notice it happening because the change is so gentle, so gradual, so patient that it moves beneath the threshold of awareness. But it is real, and it means something extraordinary, that you are not stuck, that you are never stuck, that the story your brain is telling is not a finished book but an open page, still being written, still becoming, still soft enough to hold whatever comes next. For most of the 20th century, mainstream neuroscience believed the adult brain was essentially hardwired. There is a kind of sadness in this, if you think about it. A whole century of brilliant minds looking at the most complex object in the known universe and deciding that it was finished, that it was done. That once you grew up, the brain you had was the brain you were going to keep, for better or for worse, until the very end. This belief was not born of carelessness. It came from the best tools and the best thinking available at the time. Early microscopes showed neurons as fixed, tangled structures. Early experiments suggested that damaged brain tissue could not repair itself. And so the scientific world built a story that said the brain was like a clock, assembled in youth and left to tick, unchanged, until it wound down. It was a tidy story, a neat story, but it was not the true story. The true story was quieter, and it was waiting in the wings, waiting for the right pair of eyes to see it, the right pair of hands to reach for it, the right moment in history when the old certainty would finally begin to crack. William James, in his 1890 book, The Principles of Psychology, wrote about organic plasticity of the brain decades ahead of his time. He was one of the first voices in the modern age to speak what the brain itself already knew, that it was not a fixed thing, not a finished thing, but something alive and responsive and capable of change. James was a philosopher as much as he was a psychologist, and perhaps that is why he could see what others could not. He was not bound by the rigid assumptions of the laboratory. He let his mind wander freely across the borders of science and wonder, and in doing so, he arrived at a truth that would not be widely accepted for another 100 years. He wrote that the nervous system possesses a kind of plasticity, a yielding quality, a willingness to be shaped by the forces that move through it. And though his words were largely overlooked in his own time, filed away as interesting but unproven, they planted a seed in the soil of science, a seed that would lie dormant through 2 world wars, through decades of rigid doctrine, through an entire century of certainty, before finally, at long last, beginning to bloom. In the 1960s, researchers at UC Berkeley discovered that rats raised in enriched environments developed thicker cerebral cortices than those in bear cages. This was one of the first experiments to show, in measurable physical terms, that the environment could change the structure of the brain. The researchers, Mark Rosenzweig, David Kresch, and Marion Diamond among them, placed some rats in large cages filled with toys, tunnels, wheels, and the company of other rats. Other rats were placed in bare, empty cages with nothing to explore and no companions to play with. After a period of time, the researchers examined the brains of both groups, and what they found was remarkable. The rats who had lived in the rich, stimulating world had brains that were physically different. Their cortices, the outer layer of the brain responsible for thinking, perceiving, and remembering, were measurably thicker. The neurons were larger. The connections were denser. The world they had been given to live in had literally shaped the organ they used to experience it. It was a gentle revelation found in the quiet bodies of small animals, but it carried an enormous truth that the brain does not merely observe its environment. It is built by it, shaped by it, woven from it, the way a nest is woven from the twigs of the tree it sits in. Paul Bacchi-Rita, in the late 1960s, demonstrated that the brain could learn to see through sensory substitution, using touch to replace lost vision. He was a remarkable man, a physician and neuroscientist who refused to accept the limits that his colleagues took for granted. His work began with his father, who had suffered a devastating stroke that left him paralyzed. Against the advice of nearly every expert, Bhakti Rita's brother, a physician as well, devised an intensive rehabilitation program, and their father recovered, not partially, but remarkably. He returned to teaching. He climbed mountains. He lived fully, in defiance of everything science said was possible. That experience changed Paul Bhakti Rita forever. It showed him that the brain was far more adaptable than anyone imagined. And so he built a device, a chair fitted with a grid of small vibrating pins that pressed against a person's back, translating visual images from a camera into patterns of touch. Blind participants who used this device began, over time, to perceive the world through their skin. They could detect shapes, movement, depth, not with their eyes, but through the gentle language of pressure on their backs. The brain had learned to see with a sense it was never designed to use, and in doing so it whispered a truth that still echoes through neuroscience today. The brain does not care where the information comes from. It only cares that it arrives. Michael Merzenig's research in the 1970s and 1980s on cortical maps provided some of the strongest evidence that adult brains reorganize based on experience. Merzenig is sometimes called the father of neuroplasticity, and if anyone has earned that title, it is him. Working with monkeys, he mapped the regions of the brain that corresponded to each finger of the hand. Precise, detailed maps showing which neurons fired when a particular finger was touched. And then, he did something simple and profound. He altered the input. In some experiments, he surgically joined two fingers together so that they always moved as one. In others, he trained the monkeys to use certain fingers more than others. And when he remapped the cortex afterward, the maps had changed. The brain regions corresponding to the most used fingers had expanded, while the areas for the unused fingers had shrunk. The brain had redrawn its own map, not in response to injury, but in response to experience. It had listened to the life the animal was living and quietly adjusted itself to match. This was not the plasticity of childhood. This was the adult brain reshaping itself in real time, proving once and for all that the old doctrine of the hardwired brain was not just incomplete, it was wrong. The discovery of adult neurogenesis, the birth of new neurons in adults, was confirmed in the human hippocampus in a landmark 1998 study led by Peter Eriksson and Fred Gage. For nearly the entire history of modern neuroscience, it was believed that you were born with all the neurons you would ever have. That from the moment of birth, the number could only go down, neurons could die, but new ones could never be born. It was one of the most firmly held beliefs in all of brain science. And then, at the very end of the 20th century, Eriksson and Gage showed that it was not true. Working with tissue from adult human brains, they found clear evidence that new neurons were being born in the hippocampus, the region of the brain most closely associated with memory and learning. The brain was not merely rewiring old cells, it was creating new ones. It was generating life from within itself, the way a forest floor sends up new seedlings, even in the shade of ancient trees. This discovery did not just add a footnote to neuroscience, it rewrote a chapter. It told us that the brain is not only adaptable, it is generative. It is not only flexible, it is fertile. And even in adulthood, even in old age, the quiet act of creation continues in the deepest folds of your mind. Eric Kandel won the Nobel Prize in 2000 for showing how learning changes the strength of synaptic connections, work done partly in sea slugs. There is something wonderfully humble about this, that one of the greatest insights into the human mind was found in the nervous system of a creature called Aplysia, a soft, unassuming sea slug that lives in shallow tidal waters. Kandel chose this animal precisely because its nervous system was simple, just 20,000 neurons compared to our 86 billion, and within that simplicity he could see what was hidden in our own complexity. He discovered that when the sea slug learned something, even something as basic as a reflex, the synaptic connections between its neurons physically changed. They grew stronger with repeated use, they weakened with disuse. The architecture of the nervous system was being sculpted by experience, one synapse at a time. and the molecular mechanisms he uncovered in those tiny creatures turned out to be remarkably similar to the ones at work in the human brain. Learning, at its most fundamental level, is chemistry. It is the quiet strengthening of a bridge between two cells, repeated until it holds. And for showing the world that bridge, in all its delicate molecular beauty, Kandel was awarded the Nobel Prize, a recognition that the smallest truths sometimes carry the most weight. The London taxi driver study, published by Eleanor Maguire in 2000, showed that navigating complex routes physically enlarged the hippocampus. This study has become one of the most famous and most loved in all of neuroscience, and it is easy to see why. London's streets are a labyrinth, a sprawling ancient web of roads and alleys and roundabouts that defies memorization, and yet the city's taxi drivers do memorize it. They spend years studying what is called the knowledge, a grueling test that requires them to recall thousands of routes across the city from memory. Maguire and her colleagues used brain imaging to compare these drivers with ordinary citizens, and what they found was extraordinary. The taxi drivers had significantly larger posterior hippocampi, the part of the brain responsible for spatial memory and navigation. And the longer a driver had been on the job, the larger that region was. The brain had grown to meet the demands placed upon it. It had expanded the way a muscle expands with exercise, not because it was told to, but because it was used. It is one of the most vivid demonstrations of neuroplasticity ever recorded, proof that the way you spend your days quite literally shapes the organ you use to experience them. Advances in brain imaging technology like fMRI allowed scientists to observe neuroplastic changes in living human brains for the first time. Before the arrival of functional magnetic resonance imaging, studying the brain was a bit like trying to understand the ocean by looking only at shells that washed ashore. Scientists could examine brains after death. They could study the effects of brain injuries. They could infer what was happening inside the skull from the behavior they observed outside of it. But they could not watch the brain at work. They could not see it thinking, learning, adapting, changing in real time. And then fMRI arrived, and it was as if someone had placed a window in the wall of the skull. For the first time, researchers could watch blood flow to different regions of the brain as a person performed a task. They could see which areas activated during learning, which grew quiet during rest, which expanded after practice. They could watch neuroplasticity happening, not as a theory, not as an inference, but as a living, visible, undeniable truth. The brain was no longer a locked room. It was a garden seen through glass, and everything inside it was moving, shifting, growing in ways that no one had been able to see before. By the early 2000s, neuroplasticity had shifted from a controversial idea to an accepted foundational principle of neuroscience. The journey took more than 100 years. From William James's quiet intuition in 1890, through Konorski's naming in 1948, through Merzenich cortical maps and Maguire's taxi drivers and Kandel's sea slugs, each discovery was a single thread added to a tapestry that, by the turn of the millennium, had grown too large and too beautiful to ignore. The resistance was real. For decades, scientists who championed brain plasticity were met with skepticism, dismissed as outliers, told they were wrong, and yet they kept working. They kept looking. They kept listening to what the brain was trying to tell them, and eventually the evidence became overwhelming. Textbooks were rewritten. Curricula were updated. The old doctrine of the hardwired brain was gently set aside, not with fanfare, but with the quiet acknowledgement that science, at its best, is willing to change its mind. And in that willingness, in that very act of revision, science itself demonstrated the principle it had finally come to accept. It adapted. It reorganized. It grew. Just like the brain it was trying to understand. Neurons communicate by sending electrical signals across tiny gaps called synapses. Picture, if you will, two old friends standing on opposite sides of a narrow stream. They cannot quite reach each other, but they can speak. They can send messages across the gap, small packages of meaning tossed gently through the air, caught by waiting hands on the other side. This is, in essence, what a synapse is. It is the space between two neurons, a gap so small it measures only about 20 nanometers across, far too tiny for the eye to see. And across this gap, the language of the brain is spoken. When a neuron fires, an electrical signal races down its length like a spark along a fuse. But when it reaches the synapse, the spark cannot jump. Instead, the neuron releases tiny chemical messengers, neurotransmitters, that drift across the gap and land on the surface of the neighboring cell. And if enough of these messengers arrive, the second neuron fires in turn, passing the signal onward. It is a conversation, a quiet chemical conversation happening trillions of times per second inside your head. And every thought you have ever had, every feeling you have ever felt, every dream you have ever dreamed has been carried on the wings of these tiny, invisible words. When two neurons fire together repeatedly, the connection between them strengthens, a principle often summarized as neurons that fire together, wire together. This is one of the most elegant and important ideas in all of brain science, and it is also one of the simplest to feel. Imagine two friends who talk every day. Every morning they call each other. Every evening they share a story. Over time, the bond between them deepens. The conversation becomes easier, more natural, more fluid. They begin to anticipate what the other will say. The connection grows strong not because anything dramatic happened, but simply because it was used, again and again and again, until it became second nature. Neurons work in much the same way. When two neurons fire at the same time, when one activates and the other responds over and over, the synapse between them becomes more efficient. The chemical signals are released more readily. The receiving cell becomes more sensitive. The connection physically strengthens, like a path worn smooth by footsteps. And this is the foundation of learning. This is the foundation of memory. This is how your brain takes the raw material of experience and weaves it slowly and gently into the fabric of who you are. This principle is known as Hebb's rule, named after Canadian psychologist Donald Hebb, who proposed it in 1949. Donald Hebb was not a flashy scientist. He did not make headlines or seek attention. He was a thoughtful, careful man who spent his career at McGill University in Montreal thinking deeply about how the brain learns. And in 1949, he published a book called The Organization of Behavior, in which he proposed a simple but revolutionary idea that when two neurons are active at the same time, the connection between them is strengthened. It sounds almost obvious now, like something you might have guessed on your own. But at the time, it was a profound departure from the way most scientists thought about the brain. Hebb was saying that the brain was not just a receiver of information, it was an active participant in its own wiring. It was shaping itself in response to the patterns it encountered, strengthening the connections that were used and allowing the unused ones to fade. He could not prove it with the tools available in his time. The molecular mechanisms would not be discovered for decades. But his insight was so clean, so true, so deeply in tune with what the brain was actually doing, that it became one of the most enduring principles in all of neuroscience, a quiet flame that has never gone out. Long-term potentiation is the process by which repeated stimulation of a synapse makes it more efficient at transmitting signals. If Hebb's rule is the philosophy, then long-term potentiation, or LTP as scientists call it, is the biology. It is the physical proof that connections between neurons truly do grow stronger with use. Discovered in the early 1970s by Thierry Lomo and Tim Bliss, LTP describes what happens when a synapse is activated again and again in a short period of time. The receiving neuron becomes more responsive. The signal passes through more easily. The conversation between two cells becomes quicker, clearer, more reliable, like a radio slowly being tuned to the perfect frequency until the static fades and the music comes through clean and whole. LTP can last for hours, days, or even longer, and it is widely considered one of the primary cellular mechanisms underlying learning and memory. It is the brain's way of saying, this connection matters. This path has been walked enough times to be worth keeping. And so it is kept, held in place by molecular changes so subtle and so precise that they unfold beneath the surface of awareness, like roots growing silently in the dark. The opposite process, long-term depression, weakens synaptic connections that are used infrequently. And here is the other side of the story, the quiet, necessary counterpart to strengthening. Because a brain that only strengthened connections and never weakened them would quickly become overwhelmed, tangled in its own wiring, unable to distinguish what matters from what does not. Long-term depression, which has nothing to do with emotional sadness, but everything to do with the careful housekeeping of the mind, is the brain's way of turning down the volume on connections that are no longer being used. When a synapse is rarely activated, the receiving neuron gradually becomes less responsive to it. The signal dims, the bridge narrows, the pathway fades, not with any violence or abruptness, but with the same gentle patience with which it was once built. This process is just as important as strengthening. It is what allows the brain to stay efficient, to stay focused, to clear space for the connections that are being used right now, in this moment, in this life. It is the brain's way of letting go, not with grief, but with grace, a quiet release that makes room for what is still to come. Synaptic pruning is the brain's way of removing connections that are no longer needed, making the remaining networks more efficient. Think of a rose bush in early spring. To the untrained eye, every branch looks valuable. Every shoot looks like it deserves to stay. But the gardener knows better. The gardener knows that some branches must be cut away, not because they are worthless, but because removing them allows the remaining branches to grow stronger, to bloom more fully, to direct their energy where it matters most. The brain does this too, especially during childhood and adolescence, but also throughout adulthood. The brain engages in a process of pruning, removing synaptic connections that have not been reinforced by experience. It is not destruction, it is refinement. It is the brain becoming more itself, more efficient, more specialized, by letting go of the connections it does not need. And there is something deeply reassuring about this. It means that forgetting is not a failure. Losing a skill you no longer practice is not a loss. It is the brain wisely redirecting its resources, trimming the rose bush of the mind so that the blossoms that remain can open more fully toward the light. Myelination, the process of coating nerve fibers in a fatty sheath called myelin, speeds up signal transmission and is influenced by practice and learning. Imagine a long bare wire carrying an electrical current. The signal moves, but it moves slowly, losing strength along the way. Now imagine wrapping that wire in a layer of insulation, smooth, snug, protective. Suddenly the signal moves faster. It arrives stronger. It wastes less energy along the way. This is what myelin does for the neurons in your brain. Myelin is a fatty substance, white and glistening, that wraps around the long fibers, called axons, that carry electrical signals from one neuron to the next. And the more a particular pathway is used, the more myelin is laid down along it. Practice, repetition, focused attention. These are the things that build myelin. They are the things that take a slow, uncertain signal and turn it into something fast and sure and effortless. This is why a beginner's movements feel clumsy and deliberate, while an expert's feel smooth and automatic. The expert has myelinated the pathway. The signal no longer stumbles, it flies. And every night, as you sleep, your brain is quietly adding another layer of insulation to the pathways you walked today. Dendritic spines, tiny protrusions on neurons that receive signals, can grow or shrink within hours based on experience. Of all the structures in the brain, dendritic spines may be the most delicate. They are impossibly small, each one a tiny bud on the branch of a neuron, reaching out toward the synapse like a hand reaching toward a friend, and they are remarkably responsive. Within hours of a new experience, new spines can appear, small, tentative, testing the waters of a new connection. And spines that have not received a signal in a while can shrink, pulling back, withdrawing from a conversation that has gone quiet. This speed is astonishing. The brain is not just a slow remodeler working over weeks and months. It is also a rapid responder, capable of physical change in the time it takes to learn a new fact or practice a new movement. Dendritic spines are the brain's first responders, the scouts sent out to explore new territory. And their willingness to grow, to change, to appear and disappear in response to the life you are living, is one of the most vivid and intimate expressions of neuroplasticity you will find anywhere in the body. They are proof that the brain is always listening, always adjusting, always reaching out. The brain uses neurotransmitters like dopamine, serotonin, and acetylcholine to regulate and support plastic changes. If neurons are the musicians and synapses are the spaces between them, then neurotransmitters are the notes themselves, the actual substance of the song. Dopamine, that warm golden molecule, plays a central role in motivation and reward. It tells the brain, this mattered. Remember this, do this again, Serotonin, quieter and more diffuse, helps regulate mood and emotional stability, creating the calm conditions under which learning can flourish. And acetylcholine, often overlooked but deeply important, sharpens attention and enhances the brain's ability to form new connections. It is the spotlight on the stage, illuminating the moment of learning so the brain knows where to focus its plastic efforts. Together, these chemical messengers create the internal weather of the mind, the conditions that either support or hinder the brain's ability to change. When the chemistry is right, when the right neurotransmitters are flowing in the right amounts at the right time, the brain opens like a flower and change comes easily. This is why joy helps us learn. This is why calm helps us grow. The chemistry of feeling and the chemistry of change are, in the end, the very same thing. Brain-derived neurotrophic factor, known as BDNF, is a protein that supports the survival of existing neurons and encourages the growth of new ones. If the brain is a garden, then BDNF is the rain. It is the nourishment that falls gently on every cell, encouraging growth, supporting health, keeping the soil fertile. BDNF is produced naturally in the brain, and its presence is closely linked to learning, memory, and the overall vitality of neural tissue. When BDNF levels are high, neurons are better able to survive, new connections form more easily, and the brain is more receptive to change. When BDNF levels drop, as they can during periods of chronic stress, inactivity, or poor sleep, the garden begins to dry out. Growth slows, connections weaken, the soil becomes harder to work with. This is one of the reasons why exercise is so profoundly good for the brain. Physical activity is one of the most powerful natural triggers for BDNF production. A walk through the park, a swim in cool water, even a gentle stretch before bed. These are not just good for the body. They are rain falling on the garden of the mind, softening the earth, calling forth new growth, whispering to the neurons that the conditions are right, that it is safe to reach out and grow. Glutamate is the brain's primary excitatory neurotransmitter and plays a central role in synaptic plasticity and learning. Among all the chemical messengers in the brain, glutamate is the most abundant, the workhorse, the steady presence that keeps the wheels of thought turning. When a neuron fires, it often releases glutamate into the synapse, and that glutamate binds to receptors on the neighboring cell, encouraging it to fire in turn. It is the voice that says, "Wake up, pay attention, pass the message along." And in the context of neuroplasticity, glutamate is essential. It is deeply involved in long-term potentiation, that process of synaptic strengthening we visited a few moments ago. When glutamate repeatedly activates a particular receptor called the NMDA receptor, it triggers a cascade of molecular events inside the cell that ultimately leads to a stronger, more efficient connection. It is the key that opens the door to change. But like all powerful things, it must be kept in balance. Too much glutamate can overwhelm neurons, leading to damage rather than growth. And so the brain monitors its levels with exquisite care, ensuring that just enough is released to spark learning and no more. It is a delicate act of chemistry, precise, measured, and quietly devoted to keeping you well. Neuroplastic changes can be measured at the molecular, cellular, and systems levels of the brain. This is one of the things that makes neuroplasticity so extraordinary. It is not a phenomenon that exists at just one scale. It is not something that happens only in the chemistry of a single synapse, or only in the architecture of a whole brain region. It happens everywhere, at every level, all at once. At the molecular level, proteins are being synthesized, receptors are being added or removed from the surface of neurons, and the very genes inside a cell are being turned on or off in response to experience. At the cellular level, new dendritic spines are growing, existing connections are being strengthened or pruned, and in certain regions, entirely new neurons are being born. And at the systems level, whole networks of brain regions are being reorganized, areas expanding or contracting, functions shifting from one location to another, maps being redrawn to match the life being lived. It is a symphony that plays at every octave simultaneously, and no matter where you point your attention, no matter how close you zoom in or how far you step back, the same principle holds. Change, adaptation. The quiet, ceaseless becoming of a brain that is never, ever done. The strength of a single synapse can change in as little as minutes during intense learning or experience. Minutes, not days, not weeks, not months. Minutes. When you are deeply focused, when your attention is fully absorbed in something new, when the brain senses that this moment matters, the machinery of change kicks into motion with a swiftness that can be startling. Within minutes of intense stimulation, the molecular composition of a synapse begins to shift. More receptors appear on the receiving neuron's surface. More neurotransmitter is made available for release. The connection becomes measurably stronger, measurably more efficient in the time it takes to learn a single new fact or practice a single new movement. This rapid change is often the first step in a longer process, a temporary boost that, if reinforced through repetition and sleep, will eventually become a permanent structural alteration. But the speed of that first step is remarkable. It tells us that the brain is not a slow, reluctant learner. It is eager. It is responsive. It is ready to change the moment you give it a reason to. And right now, as these words settle into your mind, somewhere inside you a synapse is shifting, quietly, gently, without asking permission, because that is simply what a living brain does. The infant brain forms more than 1 million new neural connections every second in the first few years of life. More than 1 million connections per second. Let that wash over you like warm water. In the first years of a human life, the brain is building itself at a pace that defies comprehension. Every sound the infant hears, every face they see, every texture they touch, every voice that reaches them through the soft air of a nursery, all of it is being woven into the fabric of a brand new mind. 1 million connections every second. That is the brain constructing itself in real time, laying down the foundation for everything that will come later. Language, movement, emotion, thought, imagination, love. It is the most extraordinary feat of biological engineering on the planet, and it is happening inside the skull of a baby who cannot yet speak, who cannot yet walk, who cannot yet understand a single word of what is being said. And yet, that baby's brain is doing something no supercomputer has ever done. It is building itself from scratch, using nothing but the raw material of experience, assembling a universe of connection one synapse at a time, in a quiet room, in a gentle light, in the warm shelter of someone's arms. This period of massive overproduction of synapses is called synaptogenesis. The name itself is quietly beautiful, genesis meaning birth, and synapse meaning connection, the birth of connections. And that is precisely what it is. In the earliest months and years of life, the brain produces far more synapses than it will ever need. It is as if the brain is casting an enormous net, wide, generous, indiscriminate, catching every possible pattern, every possible association, every possible thread of meaning. This overproduction is intentional. It is the brain's way of preparing for a world it has not yet fully experienced. By building an abundance of connections, the infant brain ensures that no matter what environment it finds itself in, no matter what language it will need to learn or what skills it will need to develop, the raw material is already in place. Later, through the process of pruning, the connections that are reinforced by experience will be kept, and the ones that are not will be gently removed. But in these first years, the emphasis is on abundance, on possibility, on the breathtaking generosity of a brain that builds more than it needs, just in case the world turns out to be wider and more wonderful than anyone expected. Critical periods are windows of time in early development when the brain is especially sensitive to specific types of input, such as language or vision. Imagine a window in a house that opens only at certain times of day. When it is open, the breeze flows in freely, filling the room with fresh air and the sounds of the world outside. But when it closes, the room grows still, and whatever air is inside is all there will be for a while. Critical periods are like these windows. They are specific stretches of time, often in the first few years of life, during which the brain is extraordinarily receptive to certain kinds of experience. For vision, the critical period occurs in the first year or two. For language, it extends a bit longer, reaching into early childhood. During these windows, the brain is primed to absorb the relevant input with remarkable efficiency. A child exposed to language during this period will wire their brain for it almost effortlessly. But if the window closes before the input arrives, If a child is deprived of language or visual stimulation during these crucial years, the wiring becomes much harder to establish later on. The window does not seal shut completely. The brain retains some plasticity, but the ease, the effortlessness, the wide-open receptivity of the critical period cannot be fully recaptured once it passes. During childhood, the brain is at its most plastic, which is why children often learn new languages and skills more readily than adults. Watch a child learning to speak a new language, and you will see neuroplasticity in its most natural and graceful form. There is no struggle, no conscious effort, no grammar textbook or vocabulary list. The child simply listens, absorbs, imitates, and within months, the language begins to flow from their lips as naturally as breathing. This ease is not a matter of intelligence or effort. It is a matter of biology. The child's brain is still in a state of heightened plasticity. Synapses are forming rapidly, pruning has not yet finished its work, and the neural circuitry is still soft and flexible enough to mold itself around whatever input it receives. This is why children can learn to speak 3 languages at once without confusion, why they can pick up a musical instrument and make startling progress in weeks, why they absorb the customs and rhythms of a culture simply by being immersed in it. Their brains are open in a way that adult brains are not, wide open, like a field in spring, ready to receive whatever seeds the wind carries in. It is one of the most beautiful expressions of what a brain can be when it is young and unfinished and still becoming. Synaptic pruning accelerates during adolescence, refining neural networks and making them more specialized. If childhood is the season of planting, of casting seeds in every direction and watching what grows, then adolescence is the season of tending. It is the time when the brain looks at everything it has built and begins to decide what to keep. Synaptic pruning, which has been happening since early childhood, now intensifies. The connections that have been reinforced through use are strengthened further. The ones that have not are cleared away, quietly and efficiently, like a sculptor removing the excess stone to reveal the shape that was always inside. This is why the teenage years are such a time of transformation, not just socially and emotionally, but neurologically. The brain is quite literally becoming more specialized, more refined, more streamlined. It is losing some of its childhood flexibility in exchange for something else: efficiency, speed, expertise. The wide, open field of the child's brain is becoming a well-tended garden with clear paths and defined borders and a sense of direction that was not there before. It can feel like a loss, this narrowing, but it is also a becoming. The brain is not losing itself, it is finding itself. And in the quiet work of pruning, the shape of the person begins to emerge. The prefrontal cortex, responsible for decision-making and impulse control, continues developing into the mid-20s. This is one of the more surprising truths about the human brain, that the very last region to finish maturing is the one responsible for the things we most associate with adulthood: planning, judgment, the ability to pause before acting, to weigh consequences, to choose the wiser path. The prefrontal cortex, sitting just behind the forehead like a quiet guardian, is still under construction well into a person's 20s. It is still forming connections, still myelinating its fibers, still refining the networks that will one day allow it to function with the calm, steady efficiency of a mature mind. This is not a flaw. It is not a delay or a deficiency. It is the brain's way of ensuring that the region responsible for the most complex cognitive tasks receives the most thorough preparation. A house built quickly may be finished sooner, but a house built slowly, with care, with attention, with time given to every joint and beam, will stand longer and stand stronger. The prefrontal cortex is that house. And if you are in your 20s and still feel like you are figuring things out, take comfort. Your brain is right there with you, still working, still building, still quietly putting the finishing touches on the architecture of your judgment. Neuroplasticity does not stop in adulthood. It simply becomes more targeted and experience-dependent. There is a common misconception that the adult brain is somehow finished, that the window of change closes at some point and the brain settles into a final, fixed form. But this is not true. What is true is that the nature of plasticity shifts as we age. In childhood, the brain is plastic in a broad, sweeping way, open to almost anything, shaped by everything. In adulthood, plasticity becomes more focused. It responds most strongly to experiences that are repeated, meaningful, and accompanied by attention. The adult brain does not change as easily as the child's, but it can still change profoundly. It can learn new languages, acquire new skills, form new memories, and reorganize its networks in response to the demands of life. The difference is simply that the adult brain requires a bit more intention, a bit more repetition, a bit more patience. It is like the difference between a river in spring flood, which reshapes everything in its path, and a river in summer, which carves more slowly but still, over time, moves mountains. The water is the same, the force is the same. It simply expresses itself differently in different seasons. Adults can still learn new skills, form new memories, and reorganize neural pathways, though it may require more repetition than in childhood. This is worth saying again, slowly, because it is one of the most hopeful truths in all of brain science. You can still learn, you can still change, you can still grow. It does not matter how old you are, it does not matter how long it has been since you last tried something new. The machinery of change is still inside you, still functioning, still waiting to be called upon. The adult brain may need more practice to master a new skill than a child's brain would. The path may need to be walked a few more times before it is worn smooth. But the capacity is there, fully intact, fully operational, fully yours. People in their 50s learn to play the piano. People in their 60s learn to paint. People in their 70s learn new languages and surprise themselves with how much they remember. The brain does not give up on you. It does not decide that you are too old to change. It simply asks for a little more time, a little more patience, a little more of the same gentle repetition that built every skill you have ever had. And in return, it gives you something remarkable, the knowledge that you are never finished, that every day is still an opportunity to become someone you have not been before. The aging brain shows reduced but still measurable neuroplasticity, which is why lifelong learning is beneficial for cognitive health. As the years pass, the brain does slow down in certain ways. Synapses are pruned more aggressively, myelin thins, the production of new neurons in the hippocampus declines. But, and this is the crucial word, the word that holds everything together, plasticity does not disappear, it continues. Quieter now, slower perhaps, but real. And the research is clear. The more the aging brain is used, the more resilient it remains. Learning a new craft, solving puzzles, engaging in rich conversation, reading widely, exploring unfamiliar places, all of these activities keep the machinery of plasticity engaged, keep the synapses active, keep the garden from going fallow. Lifelong learning is not a luxury, it is a form of maintenance. It is the brain's way of staying flexible in the face of time's slow march. And there is a deep kindness in this, the knowledge that the brain rewards curiosity at any age, that the simple act of remaining interested in the world is one of the most powerful things you can do for the organ that allows you to experience it. Cognitive reserve, built through education, complex work, and mentally stimulating activities, may help the aging brain compensate for neural decline. Cognitive reserve is one of the most fascinating concepts in modern neuroscience, and it offers a profound source of hope. The idea is that a lifetime of mental engagement, reading, learning, solving problems, doing complex work, maintaining rich social connections, builds a kind of buffer in the brain. A reservoir of neural resources that can be drawn upon when the brain begins to experience the natural wear of aging. People with higher cognitive reserve do not necessarily have healthier brains on a structural level. Their brains may show the same plaques, the same tangles, the same signs of decline as anyone else's, but they function better, they compensate more effectively, they find alternate pathways around the damage the way a seasoned traveller finds a detour when the main road is closed. This tells us something beautiful, that the life you live, the books you read, the conversations you have, the challenges you embrace, all of it accumulates, all of it matters. Not just in the moment, but across a lifetime. You are building a reserve right now with every thought, every question, every act of attention, and it will be there for you quietly when you need it most. Studies suggest that bilingual individuals may experience a delay in the onset of dementia symptoms, potentially due to enhanced neuroplasticity from managing two languages. There is something lovely about this finding, that the simple act of speaking two languages, of holding two systems of meaning inside one mind, may offer the brain a kind of protection against decline. Bilingual individuals constantly exercise their executive function, the set of cognitive skills responsible for switching between tasks, inhibiting irrelevant information, and holding complex rules in mind. Every time a bilingual person speaks, their brain must choose the correct language, suppress the other one, and monitor the conversation for cues about when to switch. This constant juggling act, performed thousands of times a day without conscious effort, strengthens the neural networks involved in cognitive control, and these are precisely the networks that tend to weaken in dementia. Research has suggested that bilingual individuals may show symptoms of dementia several years later than their monolingual peers, even when the physical progression of the disease is the same. The brain, it seems, has simply built more roads to get where it needs to go. And when one road is damaged, it has alternatives. It has options. It has the quiet gift of flexibility, earned through a lifetime of navigating between two worlds. Even in late adulthood, engaging in novel activities can stimulate the formation of new synaptic connections. This is the gentle truth that closes this chapter, and it is perhaps the most important one to carry with you. Novelty is a gift to the brain, at any age. Learning a new recipe, visiting an unfamiliar town, picking up a craft you have never tried before, having a conversation with someone whose perspective is different from your own. These are not small things. They are invitations to the brain to stretch, to reach, to form connections it has never formed before. The aging brain responds to novelty the way a sleeping garden responds to the first warm rain of spring, slowly at first, tentatively, but with a real and measurable awakening. New spines grow on old dendrites. New connections form between cells that have never spoken before. The landscape shifts, just slightly, just enough to remind you that the capacity for change is not something you outgrow. It is something you carry with you, always, like a seed in your pocket. And all it needs is something new, something unexpected, something that wakes the brain up gently and whispers, "There is still more to learn. There is still more to become." Learning a new skill activates specific neural circuits, and repeated practice strengthens those circuits over time. When you pick up a pen to write with your non-dominant hand, or press your fingers against the strings of a guitar for the first time, something begins to happen inside your brain that you cannot see or feel, but that is as real as the instrument in your hands. A specific set of neurons fires. A particular circuit lights up, connecting regions responsible for movement, sensation, attention, and memory. At first, the signal is weak, uncertain. The circuit has never carried this particular pattern before, and the neurons stumble over one another like musicians playing a new piece of music for the very first time. But with practice, with repetition, with patience, with the willingness to be clumsy and imperfect, the circuit strengthens, the signal clears, the neurons begin to fire in sync, and what was once difficult and deliberate begins to feel natural and easy. This is the deep magic of practice. It is not just behavioral, it is physical. Every hour you spend working at a new skill is an hour spent building new architecture inside your brain, laying down fibers and strengthening connections that will serve you for years to come. The effort is never wasted. The brain remembers every repetition, even the ones that felt like failures. The hippocampus plays a central role in forming new memories and is one of the brain regions most associated with neuroplasticity. Deep inside the temporal lobe, tucked away beneath the folds of the cortex like a small curved treasure hidden in the earth, lies the hippocampus. Its name comes from the Greek word for seahorse, because its shape, elegant, tapered, gently curving, resembles that graceful creature of the sea. And just as the seahorse moves through water with quiet determination, the hippocampus moves through the landscape of your mind, carrying new experiences from the shores of the present into the deep waters of long-term memory. Every new thing you learn, every face you remember, every place you visit for the first time, the hippocampus is there, weaving the experience into a form that can be stored and recalled. It is one of the most plastic regions of the brain, capable of generating new neurons even in adulthood, constantly reshaping itself to accommodate the flood of experience that arrives each day. Without it, new memories cannot form. The present would slide by like water through open fingers, leaving nothing behind. But with it, with this small seahorse-shaped guardian, each moment is caught, held, and gently placed into the vast library of your life. Memory consolidation, the process of stabilizing a memory after it is first formed, involves the strengthening of synaptic connections, often during sleep. When you experience something new, the memory does not simply appear in your brain fully formed, the way a photograph appears the moment you press the shutter. Instead, it arrives in a fragile state, a delicate sketch, an impression, a pattern of neural activity that is vivid but unstable. And it is during sleep that this sketch is carefully, patiently transformed into something more permanent. As you drift into the deeper stages of rest, the brain replays the day's experiences, not randomly, but with purpose. The hippocampus sends signals back to the cortex, rehearsing the patterns of the day, strengthening the connections that encode important memories and allowing the trivial ones to fade. This is why a good night of sleep can make the difference between remembering something and forgetting it entirely. This is why studying before bed is more effective than studying in the morning and then filling the day with other activities. Sleep is not the absence of learning. It is the completion of it. It is the brain's quiet finishing work, done in darkness, done in stillness, done while you are somewhere far away in dreams, trusting the mind to do what it does best. Working memory, the ability to hold and manipulate information temporarily, can be improved with targeted cognitive training. Working memory is the mental workspace, the place where you hold a phone number just long enough to dial it, where you keep the beginning of a sentence in mind while you read the end of it, where you juggle the ingredients of a recipe without looking back at the page. It is small. It is fleeting. Most people can hold only about 4 to 7 items in working memory at any given time. But research has shown that with practice, the efficiency of this workspace can be improved, not by expanding its capacity dramatically, but by strengthening the neural networks that support it. The prefrontal cortex, the parietal cortex, the pathways that connect them. Targeted training exercises, repeated over days and weeks, can lead to measurable changes in brain activity and modest improvements in working memory performance. It is not a dramatic transformation. It is a quiet one. Like strengthening the hinges on a small door so that it opens a little more smoothly, holds a little more firmly, serves its purpose a little more reliably. And in that quiet improvement, the whole architecture of thought becomes just a little bit more graceful. Musicians who practice extensively show measurable differences in brain structure, including a larger corpus callosum connecting the two hemispheres. The corpus callosum is a thick bundle of nerve fibers that connects the left and right hemispheres of the brain, a bridge of white matter that allows the two sides to communicate, to share information, to coordinate their efforts. In most people, this bridge is a certain size, a certain thickness. But in musicians, particularly those who began training early and have practiced for many years, the corpus callosum is significantly larger. The bridge is wider. The communication is richer. The two hemispheres speak to each other more fluently and more often. This makes sense when you consider what playing music requires. The left hand and the right hand must perform different tasks simultaneously. The auditory system must listen while the motor system moves. Rhythm, melody, emotion, and technique must all be coordinated in real time. To do this, the brain needs a strong, fast connection between its two halves. And so it builds one. It thickens the bridge. It lays down more fibers. It creates, through the sheer force of practice and repetition, a physical structure that would not exist if the music had never been played. The brain, in this way, is an instrument too, shaped by the songs it has been asked to carry. Learning to read physically changes the brain, creating specialized neural pathways in the visual cortex for recognizing written words. Reading is so common, so ordinary, so woven into the fabric of daily life that we rarely stop to consider what an extraordinary neurological achievement it is. Humans have been speaking for hundreds of thousands of years, but writing has existed for only about 5,000. The brain did not evolve to read. There is no reading gene, no pre-built neural circuit designed for the purpose of decoding symbols on a page. And yet we do it, effortlessly, automatically. A literate person cannot even look at a word without reading it. The brain processes the text before you have a chance to decide whether you want to. This happens because learning to read literally rewires the visual cortex, a region that originally evolved to recognize objects, faces, landscapes, the shapes of animals, is repurposed through years of practice to recognize letters and words instead. New pathways are carved into the brain's visual processing system, pathways that did not exist before literacy and that would not exist without it. Every word you have ever read has been carried along these pathways your brain built for itself, out of nothing but practice and patience and the quiet, extraordinary plasticity of the human mind. The motor cortex reorganizes when someone learns a new physical skill, such as playing an instrument or juggling. The motor cortex is a strip of brain tissue that runs across the top of the head, from ear to ear like a headband. It is the region responsible for planning and executing voluntary movements, and it contains a kind of map, a representation of the entire body, with each area of the cortex controlling a specific set of muscles. But this map is not permanent. It is not drawn in ink. It is drawn in something much softer, much more yielding, and it can be redrawn by experience. When you learn a new physical skill, when you spend hours learning to juggle or practicing a dance step or training your fingers to type without looking, the area of the motor cortex devoted to those particular movements expands. The neurons in that region recruit their neighbors, building a larger and more detailed representation of the muscles being used. The map changes to reflect the life being lived. It is as if the brain is saying, "You use these muscles more now. Let me give them more room. Let me devote more resources to making sure they work well." And so the motor cortex reshapes itself quietly and faithfully to serve the body it lives inside of. A study found that learning to juggle for 3 months led to measurable increases in grey matter in areas related to visual and motor processing. This study, conducted by researchers at the University of Regensburg in Germany, remains one of the most vivid demonstrations of experience-dependent plasticity in the adult brain. The researchers took a group of adults who had never juggled before and taught them to perform a basic 3-ball cascade. After 3 months of practice, brain scans revealed that the jugglers had developed measurably more grey matter in 2 regions, the mid-temporal area involved in processing visual motion and the posterior intraparietal sulcus involved in reaching and grasping. The brain had physically expanded in the regions that were being used most, and when the participants stopped juggling for 3 months, those same regions shrank back again, not entirely, but noticeably. The brain had let go of what was no longer being practiced. This study tells us 2 things. First, that the adult brain is fully capable of structural change in response to learning. And second, that this change is maintained only as long as the learning continues. The brain does not hoard resources. It invests them where they are needed and withdraws them when they are not. It is efficient, it is responsive, and it is, in its own quiet way, deeply honest. Spaced repetition, spreading learning sessions over time, is more effective at strengthening synaptic connections than cramming. There is a rhythm to learning, and the brain responds to it the way a garden responds to steady rain versus a sudden flood. When you cram, when you try to force everything into your memory in one long, exhausting session, the information enters the brain in a rush, overwhelming the synapses before they have had time to consolidate. Some of it sticks, but much of it washes away by morning. But when you space your learning out, when you study a little today, return to it tomorrow, revisit it again a few days later, something different happens. Each time you return, the synaptic connections are reactivated and strengthened again, layer by layer, like coats of paint on a canvas. The connection grows deeper each time because the brain has had the chance to rest between sessions, to consolidate, to prepare itself for the next encounter. This is spaced repetition, and it is one of the most well-supported findings in all of learning science. The brain does not want to be flooded. It wants to be watered gently, regularly, with patience. And when you give it that patience, it rewards you with memories that last, not for days, but for years. Retrieval practice, or actively recalling information, strengthens memory traces more effectively than passive review. It is a strange and counterintuitive truth that the act of struggling to remember something does more for your brain than the act of simply reading it again. When you passively review your notes, the information flows into your mind easily, and the feeling of familiarity tricks you into believing you know it well. But when you close the book and try to recall the information from memory, when you force your brain to search, to reach, to reconstruct what it has learned, something much deeper happens. The neural pathways that encode the memory are activated from the inside out. They are exercised, tested, strengthened by the very effort of retrieval. Each time you successfully recall a fact, the connection grows a little stronger, a little more durable, a little more resistant to forgetting. It is like the difference between watching someone walk a path and walking it yourself. One leaves you with a vague sense of the route. The other leaves you with the memory in your legs, in your bones, in the very fibers of your mind. Retrieval practice is the walking. It is the effortful, imperfect, deeply rewarding act of making the knowledge your own. Habit formation involves a shift in brain activity from the prefrontal cortex, the seat of conscious decision-making, to the basal ganglia, which governs automatic behavior. When you first begin a new habit, brushing your teeth with your non-dominant hand, taking a different route to work, learning to meditate, the effort is conscious. You have to think about it, you have to choose it, deliberately, with the full weight of your attention and your will. During this phase, the prefrontal cortex is working hard, coordinating the steps, monitoring the progress, overriding the impulse to fall back into old patterns. But over time, with enough repetition, something beautiful happens. The responsibility shifts. The prefrontal cortex, that diligent, hard-working guardian at the front of the brain, begins to hand the task over to a deeper, more ancient structure, the basal ganglia, which sits nestled in the center of the brain like a quiet keeper of routine. And once the basal ganglia takes over, the behavior becomes automatic. You no longer have to think about it. You no longer have to choose it. It simply happens, the way breathing happens, the way blinking happens, woven into the fabric of your day without effort or deliberation. This is the neurological signature of a habit, and it is one of the most practical and empowering expressions of neuroplasticity you will ever encounter. The brain's ability to automate repeated actions through plasticity is what allows skilled performers to act without conscious thought. Watch a concert pianist's hands as they move across the keys. Watch a professional athlete's body as it responds to a ball in flight. Watch a seasoned driver navigate a complex highway exchange without a moment's hesitation. In each of these cases, what you are witnessing is the result of thousands upon thousands of hours of practice distilled by the brain into something that looks effortless. The neural circuits responsible for these actions have been strengthened so many times, myelinated so thoroughly, automated so completely that they no longer require the involvement of the conscious mind. The prefrontal cortex, which once had to supervise every step, has stepped aside. The signals now flow along pathways so well-worn and so fast that the performer can act with a fluidity and a speed that conscious thought could never match. This is mastery, and it is, at its root, a story of neuroplasticity, of a brain that took something clumsy and uncertain and through the patient alchemy of repetition transformed it into something beautiful. The skill lives in the brain now, woven into its very structure, and it moves through the body like water through a stream bed that has been carved over years to exactly the right depth and shape. Mental rehearsal, vividly imagining performing an action, can activate many of the same neural pathways as physically performing it. Close your eyes for a moment and imagine lifting your hand. Imagine the feeling of your fingers curling, the weight of your arm rising through the air, the gentle tension in your shoulder. You did not move. Your hand stayed still. But inside your brain, something real just happened. The motor cortex fired. The neural circuits responsible for moving your hand were activated, not as strongly as they would be during actual movement, but measurably, meaningfully, detectably. This is the power of mental rehearsal. When you vividly imagine performing an action, the brain treats the imagined experience as partially real. It runs the same circuits, engages the same networks, practices the same pathways, all without a single muscle contracting. Athletes have used this for decades. A diver imagines the perfect dive before stepping to the edge. A basketball player visualizes the arc of the ball before the free throw. And the research supports them. Studies show that mental rehearsal, when combined with physical practice, can improve performance more than physical practice alone. The brain, it seems, does not fully distinguish between what is done and what is vividly imagined, And in that blurred boundary between thought and action, neuroplasticity finds yet another doorway through which to do its quiet, extraordinary work. During sleep, the brain replays and consolidates the day's learning, strengthening important neural connections. As you drift towards sleep tonight, something remarkable will begin to happen. The brain, freed from the demands of the waking world, will turn its attention inward and begin the slow, careful work of sorting through everything you experience today. Moments that mattered will be replayed, not as dreams necessarily, but as patterns of neural activity echoing through the hippocampus and the cortex in quiet repetition. The connections that carried today's learning will be reactivated, tested, strengthened. The ones that are no longer needed will be gently dimmed. It is as if the brain waits all day for this moment, waits for you to close your eyes and let go so that it can finally sit down with the raw material of your life and begin shaping it into something lasting. This is consolidation. This is the invisible craftsmanship of sleep, and it means that the rest you are approaching right now is not passive. It is not empty. It is one of the most productive and important things your brain will do in the next 8 hours. You are not stepping away from the work of living, you are stepping into the work of becoming. Slow-wave deep sleep is particularly important for memory consolidation and synaptic homeostasis. Among the stages of sleep, slow-wave sleep, the deep, dreamless phase that comes in the first half of the night, is perhaps the most restorative for the brain. During this stage, broad, synchronized waves of electrical activity sweep across the cortex like gentle tides moving over a shore. And within these waves, the brain is performing 2 essential tasks. The first is memory consolidation, the replaying and strengthening of the day's most important learning. The second is synaptic homeostasis, a process proposed by Giulio Tononi and Chiara Cirelli, which suggests that during deep sleep, the brain slightly weakens all synaptic connections across the board. This sounds counterintuitive, but it is deeply purposeful. During the day, as you learn and experience, synapses are continuously strengthened. If this process went on unchecked, the synapses would eventually become saturated, too strong, too rigid, too loud. Slow-wave sleep gently turns down the volume on everything, resetting the system so that it is ready to learn again tomorrow. It is the brain's way of clearing the slate, of taking a breath, of preparing the garden for a new day of growth. And the deeper your sleep, the more thoroughly this quiet work is done. The glymphatic system, most active during sleep, clears metabolic waste from the brain, supporting healthy neural function. While you sleep, something almost miraculous happens beneath the surface of your brain. A network of channels wrapped around the blood vessels of the central nervous system opens wide, much wider than during waking hours, and begins to flush fluid through the brain tissue, carrying away the metabolic waste that accumulated during the day. This network is called the glymphatic system, a name that nods to the glial cells that make it possible and the lymphatic system it resembles. Among the waste products it clears is beta amyloid, a protein that, when it builds up in excess, is associated with Alzheimer's disease. During deep sleep, the glymphatic system operates at its peak, washing through the brain with a thoroughness that is simply not possible when you are awake. It is as if the brain waits for you to fall asleep, then opens the floodgates and washes itself clean, gently, methodically, with the quiet devotion of a caretaker tending to a beloved home. This is one of the most compelling reasons to protect your sleep, not just for energy, not just for mood, but for the long-term health of the very organ that makes you who you are. Sleep deprivation impairs neuroplasticity, reducing the brain's ability to form and retain new connections. When sleep is cut short, the effects ripple through every system of the brain like a stone dropped into still water. Attention falters, memory weakens, emotional regulation becomes fragile, and beneath all of these visible symptoms, something deeper is happening. The machinery of plasticity itself is being compromised. Without adequate sleep, the brain cannot properly consolidate the day's learning. Long-term potentiation and the process that strengthens synaptic connections is impaired. The production of BDNF, that essential protein that nourishes neural growth, declines. The glymphatic system cannot fully clear the accumulated waste. Even a single night of poor sleep can reduce the brain's ability to form new connections the following day. And chronic sleep deprivation compounds the damage, creating a deficit that accumulates over weeks and months. This is not said to frighten you, it is said to honor you, to remind you that the rest you are seeking right now is not indulgence, it is necessity. It is one of the most important gifts you can give your brain. And the fact that you are here, allowing yourself to slow down, to breathe, to drift, that is already a step toward the kind of care your mind most needs. Aerobic exercise increases the production of brain-derived neurotrophic factor, that key protein supporting neuroplasticity. When you move your body, when you walk briskly through a park, swim laps in a quiet pool, ride a bicycle down a tree-lined road, something wonderful happens inside your brain. The heart beats faster, blood flows more vigorously through the vessels of the brain, and in response the brain begins to produce more BDNF, that precious protein we visited earlier, the one that acts like rain on the garden of the mind. BDNF nourishes existing neurons, helps new ones survive, and strengthens the connections between cells. And aerobic exercise is one of the most powerful and reliable ways to increase its production. Study after study has confirmed this. People who exercise regularly have higher levels of BDNF, better memory performance, and larger hippocampal volumes than those who are sedentary. The brain, it turns out, is not separate from the body. It does not sit in the skull, detached and indifferent to what happens below the neck. It is deeply, intimately connected to the physical life of the organism it inhabits. And when the body moves, the brain blooms. When the heart pumps, the mind grows. They are partners in the quiet project of keeping you alive and capable and whole. Regular physical exercise has been shown to increase the volume of the hippocampus in older adults. This finding comes from a landmark study conducted by Kirk Erickson and colleagues at the University of Pittsburgh, and it carries a message of deep hope for anyone concerned about the aging brain. The researchers took a group of older adults and assigned half of them to a program of moderate aerobic exercise, walking 3 times a week for 40 minutes at a time. The other half engaged in a stretching and toning program that raised the heart rate only minimally. After 1 year, the walkers showed a measurable increase in the volume of their hippocampus, the brain's memory center, while the stretching group showed the typical age-related decline. The walkers' hippocampi had effectively reversed 1 to 2 years of normal aging, not through medication, not through surgery, but through the simple, ancient act of walking. There is something profoundly reassuring about this. The remedy is not exotic, it is not expensive. It is available to almost everyone, and it has been available since the beginning of human history. Walking, moving, putting one foot in front of the other, and in that humble act, the brain finds the nourishment it needs to hold on to what matters most. Exercise promotes neurogenesis, the birth of new neurons, particularly in the hippocampus. Of all the discoveries in modern neuroscience, this may be one of the most astonishing, that physical exercise can actually cause the brain to produce new neurons. Not just strengthen existing connections, not just protect what is already there, but create something entirely new. Research in both animals and humans has shown that aerobic exercise stimulates the production of new neurons in the hippocampus, the region of the brain most closely tied to learning and memory. These newborn neurons integrate into existing circuits, forming fresh connections, adding new capacity to the brain's already remarkable network. In animal studies, the effect is striking. Mice given access to a running wheel produce significantly more new hippocampal neurons than sedentary mice, and the behavioral effects are equally clear. The exercising animals perform better on tests of learning and memory. The message is simple, and it is old, and it is true. Movement gives life, not just to the muscles and the heart and the lungs, but to the very cells of the brain. Every step, every swim, every gentle jog is an invitation to the hippocampus to do what it does best, to grow, to build, to create something new out of the raw material of motion. Even a single session of moderate exercise can temporarily improve cognitive flexibility and learning. You do not need to train for a marathon. You do not need to commit to months of discipline before your brain begins to benefit. A single session of moderate exercise, a brisk walk, a bike ride, a swim, can produce measurable improvements in cognitive function that very same day. Studies have shown that after just 20 to 30 minutes of moderate aerobic activity, people perform better on tests of attention, working memory, and cognitive flexibility, the ability to switch between tasks and adapt to new rules. The effects are temporary, lasting a few hours at most, but they are real and they are immediate. The brain responds to movement the way a window responds to being opened. The fresh air rushes in at once. Blood flow increases, neurotransmitters are released, BDNF levels rise, and the neural networks responsible for learning and attention become, for a brief window, sharper and more receptive. This is one of the most practical and accessible truths in all of neuroscience, that you do not need to change your entire life to give your brain a boost. You just need to move, even once, even for a little while, and the brain will thank you for it before the afternoon is over. Chronic stress elevates cortisol levels, which can impair neuroplasticity and even shrink the hippocampus over time. Stress, in small doses, is not the enemy. A brief burst of stress, the kind that sharpens your focus before a presentation or quickens your step when you are running late, can actually enhance alertness and even support short-term memory. But when stress becomes chronic, when the alarm system of the body stays activated for weeks, months, years without relief, the picture changes dramatically. Chronic stress floods the brain with cortisol, a hormone that, in sustained high levels, is toxic to the very structures that support learning and memory. The hippocampus, rich in cortisol receptors, is particularly vulnerable. Prolonged exposure can cause dendritic branches to retract, synaptic connections to weaken, and the overall volume of the hippocampus to shrink. Neurogenesis slows, plasticity is impaired. The garden of the mind, bathed too long in the harsh chemistry of fear, begins to pull inward, to withdraw, to close. This is not a permanent sentence. The brain can recover. When the stress is relieved, when calm returns, the hippocampus can regrow, connections can be rebuilt, plasticity can resume. But it is a reminder, a gentle, important reminder, that peace is not a luxury. It is a biological necessity. And the calm you are allowing yourself right now, in this quiet moment, is doing more for your brain than you may realize. Mindfulness meditation has been shown to increase grey matter density in brain regions associated with self-awareness, compassion, and introspection. The practice of mindfulness, of sitting quietly, paying attention to the breath, observing thoughts without judgment, has been practiced for thousands of years in contemplative traditions around the world. And in recent decades, neuroscience has begun to confirm what meditators have long reported, that the practice changes the brain. Studies using MRI have shown that people who meditate regularly have increased grey matter density in several key brain regions, including the prefrontal cortex, the insula, and the temporoparietal junction, areas involved in self-awareness, empathy, and the ability to take another person's perspective. The brain, it seems, responds to the practice of paying attention the same way it responds to any other form of repeated experience, by strengthening the circuits that are being used. When you practice noticing your breath, the circuits for interoceptive awareness grow stronger. When you practice observing your thoughts without reacting, the circuits for emotional regulation are reinforced. Meditation does not add anything foreign to the brain. It simply cultivates what is already there. The capacity for presence, for awareness, for a kind of quiet, tender attention to the moment you are in. And the brain, grateful for the practice, reshapes itself to hold that attention more easily. A study from Harvard found that 8 weeks of mindfulness practice led to measurable changes in brain structure, including increased cortical thickness. 8 weeks. That is all it took. In a study led by Sarah Lazar at Massachusetts General Hospital and Harvard Medical School, participants who had never meditated before were guided through an 8-week mindfulness-based stress reduction program. They practiced for an average of about 27 minutes a day, and at the end of those 8 weeks, MRI scans revealed measurable increases in grey matter concentration in the hippocampus, the brain's memory center, and in the temporoparietal junction, a region involved in empathy and perspective-taking. At the same time, grey matter density decreased in the amygdala, the brain's alarm system, and this decrease was correlated with reductions in self-reported stress. The brain had physically changed, not after years of monastic practice, but after 2 months of sitting quietly and paying attention to the breath. There is something deeply encouraging in this finding. It tells us that the brain is listening, that it is responsive to even modest, consistent efforts, that you do not need to upend your life to change your mind. You only need to show up quietly, regularly, and let the practice do its work. The brain will take care of the rest. Nutrition also affects neuroplasticity. Omega-3 fatty acids, found in fish and certain nuts, support synaptic function and neural membrane health. The brain is, at its most fundamental level, a physical organ, built from the same raw materials that build the rest of the body. And just as muscles need protein and bones need calcium, neurons need specific nutrients to function at their best. Among the most important are omega-3 fatty acids, particularly a form called DHA, which makes up a significant portion of the cell membranes in the brain. These fatty acids keep the membranes fluid and flexible, which is essential for the proper functioning of synapses. When omega-3 levels are adequate, neurotransmitters are released and received more efficiently. Synaptic plasticity is enhanced. BDNF production is supported. And when omega-3 levels are low, the opposite begins to happen. Membranes stiffen, signaling slows, and the brain's capacity for change is diminished. This is why diets rich in fatty fish, walnuts, flax seeds, and other sources of omega-3s have been consistently linked to better cognitive health. The brain is asking, in its quiet way, to be fed well, to be given the materials it needs to do the work of thinking, learning, remembering, and changing. And when those materials arrive, the brain responds with the only gratitude it knows, by working better, by lasting longer, by continuing to grow. After a stroke, the brain can partially reorganize so that healthy areas take over functions previously managed by the damaged region. A stroke is a sudden, devastating event, a blockage or rupture in a blood vessel of the brain that cuts off oxygen to a region of neural tissue, causing cells to die within minutes. The damage can be profound. Movement can be lost, speech can be impaired, memory, perception, emotion. Any of these can be affected depending on which part of the brain is harmed. And yet, in the days and weeks and months that follow, something extraordinary often begins to happen. The brain starts to reorganize. Healthy regions, unaffected by the stroke, begin to take on some of the functions that were lost. New neural pathways are forged, detours around the damage, alternative routes that the brain discovers and strengthens through effort and repetition. This reorganization is not automatic. It requires work, often intensive rehabilitation, guided by therapists who understand the principles of plasticity. But the potential is there. The brain does not accept the damage as final. It searches for another way. It reaches across the lesion, around the silence, toward function and recovery and life. And in many cases it finds it, not perfectly, not completely, but meaningfully, beautifully, against all the odds that the old doctrine of the fixed brain would have predicted. Constraint-induced movement therapy, which forces use of an affected limb after stroke, harnesses neuroplasticity to restore motor function. This therapy was developed by neuroscientist Edward Taube, and it is one of the most powerful practical applications of neuroplasticity in clinical medicine. The idea is deceptively simple. After a stroke that impairs the use of one arm or hand, patients naturally begin using the unaffected limb for everything, a behavior called learned non-use. The damaged pathways deprived of practice weaken further. The brain, following the principle of use it or lose it, begins to reassign the cortical territory that once controlled the affected limb. Constraint-induced therapy reverses this process. The healthy limb is restrained, placed in a sling or a mitt, and the patient is required to use the affected limb for hours each day, performing repetitive task-specific exercises. The effect is remarkable. Forced to use the weakened limb, the brain begins to reorganize. New connections form, the cortical map expands, motor function improves, sometimes dramatically, even years after the stroke occurred. It is neuroplasticity harnessed with intention, the brain being gently, firmly shown that the old pathway still matters, that it is still worth maintaining, that the effort of reaching for a cup or buttoning a shirt is enough to rebuild what was nearly lost. Rehabilitation after brain injury is most effective when it is intensive, repetitive, and task-specific, principles rooted in neuroplasticity. This is one of the most important lessons that neuroplasticity has taught the medical world, that recovery from brain injury is not a passive process. It is not something that simply happens or does not happen based on the severity of the damage alone. It is something that can be actively encouraged, cultivated, and guided. And the principles that guide it are the same principles that underlie all neuroplastic change: repetition, intensity, and specificity. The brain changes in response to what it does, not in response to what it intends to do or hopes to do. To rebuild a lost function, the patient must practice that specific function over and over with enough intensity and enough repetition to convince the brain that this pathway is worth rebuilding. A stroke patient who wants to regain the use of their hand must practice using their hand, not just once, not just occasionally, but repeatedly, daily, with focused determination. And when they do, the brain responds. It lays down new connections, it recruits healthy tissue, it begins, slowly and patiently, to rebuild what was damaged. The brain does not ask for miracles, it asks for practice, and in that practice it finds the raw material for its own remarkable recovery. Phantom limb sensations occur because the brain's body map reorganizes after limb loss, with neighboring regions expanding into the vacated cortical area. When a person loses a limb through amputation or injury, the region of the brain that once received sensory information from that limb does not simply go silent, it does not shut down or fade away. Instead, the neighboring cortical regions, still receiving input from adjacent body parts, begin to expand into the vacated territory. The brain's body map redraws itself, filling the empty space with signals from nearby areas. This is why many amputees report feeling sensations in their missing limb when other parts of their body are touched. A person who has lost a hand may feel a phantom finger when their face is stroked, because the cortical region for the face has expanded into the territory once devoted to the hand. These phantom sensations are not imaginary. They are the direct result of cortical reorganization, the brain doing what it always does, which is to make use of every available resource. It is neuroplasticity in one of its most vivid and sometimes most painful forms, a reminder that the brain never stops adapting, even to loss, even to absence, even to the silence where a limb used to be. Cochlear implants work in part because the auditory cortex can adapt to interpret electronic signals as sound through neuroplastic reorganization. A cochlear implant is a small electronic device that is surgically placed in the inner ear to provide a sense of sound to a person who is profoundly deaf. But the signal it delivers is not the same as natural hearing. It is a rough translation, a set of electronic pulses that represent the frequencies and patterns of speech and sound, but that are far simpler and far cruder than the rich, detailed signals the ear normally sends to the brain. And yet, over time, many cochlear implant recipients learn to understand speech remarkably well. They can follow conversations, recognize voices, appreciate music. How is this possible when the signal is so impoverished compared to natural sound? The answer is neuroplasticity. The auditory cortex, receiving this new and unfamiliar input, gradually reorganizes itself to make sense of it. It learns the new language. It adapts its circuitry to extract meaning from the electronic patterns, filling in the gaps, refining its interpretations, growing more fluent with each passing week and month. It is the brain doing what it has always done, taking whatever input it receives and making the best possible sense of it. The implant provides the signal, but it is the brain, through the quiet miracle of plasticity, that provides the understanding. People who lose their sight often experience cross-modal plasticity, where the visual cortex is recruited for processing touch or sound. When the eyes can no longer send their signals, when blindness arrives, whether at birth or later in life, the visual cortex does not simply retire. It does not go dark and sit idle for the rest of the person's life. Instead, in one of the most remarkable demonstrations of neural flexibility ever documented, it begins to take on new responsibilities. In blind individuals, the visual cortex has been found to become active during tasks that have nothing to do with vision, listening to speech, reading Braille, navigating by sound. The region of the brain that was built to see has been repurposed to feel and to hear. This is cross-modal plasticity, and it tells us something profound about the nature of the brain. The visual cortex is not, in the deepest sense, a seeing organ. It is a processing organ. a region of tissue optimized for handling complex patterns of information. And when visual information is no longer available, it happily applies that processing power to other senses. The brain does not waste its resources. It does not leave rooms empty. It fills them. It uses them. It finds a way to make every part of itself useful, no matter what the circumstances, no matter what has been lost. Studies of blind Braille readers show that their visual cortex becomes active during tactile reading, a striking example of cortical reassignment. This finding has fascinated neuroscientists for decades, and it remains one of the most compelling pieces of evidence for the brain's extraordinary flexibility. When a person who has been blind from birth reads Braille, running their fingertips across the raised dots of a page, the region of their brain that would normally process visual information lights up with activity. The visual cortex, receiving no input from the eyes, has been recruited for the task of interpreting touch, and it does so with remarkable efficiency. In fact, research has shown that if the visual cortex of a blind Braille reader is temporarily disrupted, using a technique called transcranial magnetic stimulation, their ability to read Braille is impaired. This means the visual cortex is not just passively involved, it has become essential to the task. It has been so thoroughly reassigned that the person depends on it for a skill that has nothing to do with vision. The brain has rewritten its own job descriptions. It has looked at the resources available and the tasks that need to be done, and it has made a decision, not consciously but through the slow, steady logic of plasticity, to put every region to its best possible use. Cognitive behavioral therapy has been shown to produce measurable changes in brain activity and structure, demonstrating that changing thought patterns can physically reshape neural circuits. This is one of the most powerful and most hopeful findings in modern neuroscience, that the way you think can change the physical structure of your brain. Cognitive behavioral therapy, or CBT, is a form of psychotherapy that helps people identify and change unhelpful patterns of thought and behavior. It teaches people to notice when they are caught in distorted thinking, catastrophizing, overgeneralizing, assuming the worst, and to gently, systematically replace those patterns with more balanced and accurate ones. And the research shows that when people engage in this process consistently, their brains change. Brain imaging studies have revealed that CBT can reduce activity in the amygdala, the brain's fear center, and increase activity in the prefrontal cortex, the region responsible for rational thought and emotional regulation. The neural circuits that once fired automatically in response to perceived threats begin to quiet. New circuits, built through practice and repetition, take their place. It is the same principle that underlies all neuroplasticity. Neurons that fire together, wire together. But here, the firing is not driven by a physical skill or a sensory experience. It is driven by a thought, a deliberate, chosen, practiced thought. And the brain, unable to distinguish between a thought and any other form of experience, reshapes itself accordingly. Neuroplasticity is a key principle underlying many forms of psychotherapy and behavioral rehabilitation. If CBT is one expression of this truth, it is far from the only one. Across the wide landscape of therapeutic practice, from exposure therapy to dialectical behavior therapy, from trauma-focused interventions to mindfulness-based approaches, the underlying mechanism is the same. All of these therapies work, at least in part, because the brain can change. Because the neural pathways that encode fear, anxiety, depression, and maladaptive behavior are not permanent fixtures. They are learned patterns, connections strengthened through repetition, exactly the same way any other connection is strengthened. And what has been learned can, with patience and practice, be unlearned. New associations can be formed, new pathways can be built. The old circuits, deprived of the repetitive activation that sustained them, can gradually weaken and fade. This is not to say that therapy is easy or that change comes quickly. It does not. The pathways of anxiety and fear have often been reinforced for years, and they do not yield without effort. But the principle is sound, and the evidence is clear. The brain is capable of being rewritten, not erased, not reset, but gently, patiently rewritten. One new thought, one new choice, one new experience at a time. And that is enough. That is always enough. Exposure therapy for phobias and PTSD works by gradually forming new neural associations that compete with and weaken fear-based connections. Fear is one of the brain's most powerful and most ancient responses. When a threatening experience is encoded, the sound of a car crash, the sight of a spider, the memory of a moment of helplessness, the neural circuits that store that fear are built quickly and built strong. The amygdala, the brain's alarm system, fires with urgent intensity, and the body responds before the conscious mind even has time to think. This is by design. Fear is meant to protect you, but sometimes the alarm becomes too sensitive. It fires in response to things that are not truly dangerous. A harmless spider, an elevator, a crowded room, and the more the fear is avoided, the stronger the circuit becomes, until it begins to control the shape of a person's life. Exposure therapy addresses this by gradually, carefully introducing the feared stimulus in a safe environment. The person faces the spider, rides the elevator, enters the room, and survives. And each time they survive, a new neural association is formed. Safety, not danger. Calm, not panic. These new associations do not erase the old fear circuit, but they compete with it. They offer the brain an alternative pathway, and with enough repetition, the alternative begins to win. The alarm quiets. The fear loosens its grip, and the brain, once again, demonstrates its most essential quality, the ability to learn something new, even when something old is trying very hard to hold on. The brain's ability to compensate after injury tends to be greater when rehabilitation begins early, though improvements can occur even years later. Timing matters in rehabilitation, but it is not everything. The weeks and months immediately following a brain injury are often described as a window of heightened plasticity, a period when the brain is most responsive to therapy, most willing to reorganize, most capable of rapid change. During this acute phase, the brain is actively engaged in repair processes. Inflammation is being managed, surviving neurons are adjusting their activity, and the chemical environment of the injured tissue is primed for reorganization. Starting rehabilitation during this window takes advantage of these natural processes and can lead to faster, more significant gains. But here is the part that matters most, the part that must not be lost in the emphasis on early intervention. Improvement is possible at any time. People who begin rehabilitation months or even years after an injury can still make meaningful progress. The brain does not close the door on change. It may narrow the opening. It may require more effort, more repetition, more time, but the capacity for reorganization persists. There is no expiration date on neuroplasticity. There is no point at which the brain declares itself finished and refuses to try. As long as the effort is made, the brain will answer. Maybe not as quickly, maybe not as dramatically, but it will answer. Transcranial magnetic stimulation, or TMS, can be used to modulate neuroplasticity and is being explored as a treatment for depression and other conditions. Transcranial magnetic stimulation is a non-invasive technique that uses magnetic fields to stimulate specific regions of the brain. A coil is placed against the scalp, and brief magnetic pulses are delivered, passing painlessly through the skull and inducing small electrical currents in the underlying brain tissue. These currents can either increase or decrease the activity of the targeted neurons, depending on the pattern and frequency of the stimulation. And because neuroplasticity is driven in part by neural activity, TMS can be used to nudge the brain's plastic processes in a desired direction. In the treatment of depression, repetitive TMS is applied to the left dorsolateral prefrontal cortex, a region that tends to be underactive in people with depression. By increasing activity in this area, TMS can help restore the balance of neural circuits involved in mood regulation. The effects are not instant. They build over multiple sessions as the repeated stimulation gradually strengthens the targeted pathways. It is neuroplasticity guided by technology, a gentle electromagnetic hand reaching through the skull to help the brain help itself. And while TMS is not a cure for every condition, it represents something beautiful about the direction of modern medicine. The willingness to work with the brain's own capacity for change rather than against it. The brain's sensory maps are not fixed. They can expand or contract depending on how much a particular sense is used. Inside your brain there is a map of your body, not a map you could draw on paper, but a map written in neurons, a representation of every surface, every joint, every fingertip laid out across the cortex in an orderly, organized fashion. This map was first described by neurosurgeon Wilder Penfield in the 1930s, and his drawings of it, the famous homunculus with its enormous hands and lips and tiny torso, have become icons of neuroscience. But what Penfield did not fully appreciate at the time was that this map is not permanent. It is alive. It breathes. It changes. The regions devoted to the most used body parts expand, while the regions for the least used parts contract. A violinist's cortical map devotes more space to the fingers of the left hand. A person who reads Braille has an enlarged representation of the reading finger. The map adjusts itself to match the life being lived, expanding where attention is focused and withdrawing where it is not. It is the brain's way of allocating its resources wisely, of giving the most space to the parts of the body that need it most. And it means that the map you carry inside your head right now is uniquely yours, shaped by your habits, your skills, your history, your touch. In musicians who play string instruments, the cortical representation of the fingers on their left hand is measurably larger than in non-musicians. This finding, first reported by Thomas Elbert and colleagues in the mid-1990s, is one of the most elegant demonstrations of use-dependent plasticity in the human brain. String players, violinists, cellists, guitarists use the fingers of their left hand with extraordinary precision and frequency. Each finger must find its exact position on the string, press with the right amount of force, vibrate at the right speed, and move to the next position in a fraction of a second. The demands are immense, and the brain responds accordingly. Brain imaging studies have shown that the somatosensory cortex, the region that processes touch from the fingers, devotes significantly more space to the left-hand fingers in string players than in people who do not play. And the earlier in life the musician began training, the larger this expansion tends to be. The brain has sculpted itself around the demands of the instrument. It has given more room, more neurons, more processing power to the fingers that need it most. It is a beautiful example of the brain meeting the musician halfway, the musician providing the hours of practice and the brain providing the physical architecture to make that practice count. Sensory substitution devices can allow the brain to interpret visual information through touch or sound, demonstrating cross-modal plasticity. Building on the pioneering work of Paul Bacchi-Rita, modern sensory substitution devices have taken the concept even further. Today, devices exist that convert visual images into patterns of sound or vibration, allowing blind individuals to navigate their environment using senses other than sight. One such device, the voice, translates images captured by a camera into a complex soundscape. Height is represented by pitch, brightness by volume, and position by the timing of the sound. Users who train with this device over weeks and months report a gradual shift in their experience. What begins as a confusing wash of sound slowly resolves into something that feels remarkably like seeing. They can detect the shapes of objects, the outlines of rooms, the movements of people. The brain, receiving this unfamiliar input, has learned to decode it, to extract spatial meaning from auditory data, to build a picture of the world from sound. This is cross-modal plasticity at its most vivid and most hopeful. It tells us that the brain does not define itself by its inputs. It defines itself by its ability to make sense of whatever inputs it receives. And that ability, honed by millions of years of evolution, is far more flexible and far more generous than anyone once believed. After even short periods of blindfolding, sighted individuals show increased activation of the visual cortex during tactile tasks, evidence of rapid plastic change. This finding is astonishing in its speed. In studies where sighted participants were blindfolded for as little as 5 days, brain imaging revealed that their visual cortex, the region normally reserved for processing sight, began responding to touch. When these blindfolded participants performed tactile tasks such as reading Braille-like patterns with their fingers, their visual cortex showed measurable activation. The brain, deprived of visual input for less than a week, had already begun to reassign its resources. And when the blindfold was removed, the effect disappeared within hours. The visual cortex returned to its usual role, as if nothing had happened. This tells us something remarkable about the brain's flexibility. The capacity for cross-modal reorganization is not something that takes years to develop. It is always there, just beneath the surface, ready to be called upon the moment circumstances change. The brain is not waiting for a crisis to begin adapting. It is adapting constantly, in real time, with a readiness and a responsiveness that challenges everything we once assumed about the stability of cortical function. Even now, in this quiet moment, your brain is poised and ready to shift, to adjust, to meet whatever the next moment brings. The McGurk effect, where visual speech cues alter what we hear, demonstrates how the brain constantly integrates and reweights sensory input. If someone plays a recording of the syllable BA while showing you a video of a person mouthing the syllable GAR, you are very likely to hear something in between. Day. This is the McGurk effect, and it reveals something profound about the way the brain constructs your experience of the world. You do not hear with your ears alone, you do not see with your eyes alone. The brain takes input from every available sense and blends them together into a single, unified experience. And it does so in real time, seamlessly, without your conscious awareness. When two senses disagree, the brain does not simply choose one, it compromises. It creates a perception that is a blend of both, weighted by whichever sense it considers more reliable in that moment. This constant reweighting, this ongoing negotiation between the senses, is itself a form of plasticity, the brain adjusting its interpretation of the world moment by moment, adapting to the information available, always searching for the most coherent story it can tell. You experience the world not as it is, but as your brain, in its infinite adaptive wisdom, believes it to be. Perceptual learning, becoming better at detecting fine differences in stimuli, is driven by plastic changes in sensory cortices. A wine sommelier can detect the faintest note of blackcurrant in a glass of Bordeaux. A master tailor can see the difference between two shades of navy that look identical to the untrained eye. A musician can hear a note that is a fraction of a semitone off pitch. These abilities are not born. They are built, slowly, carefully, through thousands of hours of focused practice. And they are built in the brain, in the sensory cortices that process taste, sight, and sound. This process is called perceptual learning, and it is one of the subtlest and most beautiful forms of neuroplasticity. With enough practice, the neurons in the relevant sensory cortex become more finely tuned, more discriminating, more capable of detecting differences that once seemed invisible. The change is not dramatic, it is gradual, incremental, unfolding over months and years of quiet attention. But the result is a perceptual world that is richer, more detailed, more nuanced than the one experienced by a novice. The expert does not see a different world. They see the same world, but with greater resolution. The brain, through the patient alchemy of practice, has turned up the sensitivity on its own instruments. The brain can recalibrate its sense of body ownership remarkably quickly, as demonstrated by the rubber hand illusion. In this now classic experiment, a person sits with one hand hidden behind a screen while a rubber hand is placed in front of them, positioned where their real hand would normally be. A researcher then simultaneously strokes both the hidden real hand and the visible rubber hand with a paintbrush using identical movements. After just a minute or two, something uncanny happens. The person begins to feel as though the rubber hand is their own. They feel the brush touching the rubber hand, not the real one. And if the researcher suddenly strikes the rubber hand with a hammer, the person flinches. Their body reacts as though the rubber hand is truly part of them. This illusion reveals something extraordinary about the brain's model of the body. It is not fixed. It is not anchored permanently to the physical borders of the flesh. It is a construction, a best guess assembled from visual and tactile cues, updated continuously and capable of being recalibrated in moments. The brain decides what belongs to you based on the information it receives, and when that information changes, the brain's model of your body changes too, swiftly, seamlessly, without asking for your permission or your opinion. Chronic pain can involve maladaptive neuroplasticity, where the brain's pain circuits become amplified even after the original injury has healed. Pain is one of the brain's oldest and most essential signals, a warning that something is wrong, that tissue is being damaged, that action must be taken. But sometimes the pain outlasts the injury. Sometimes, long after the wound has healed and the tissue has recovered, the brain continues to produce pain. This is chronic pain, and it is one of the most challenging consequences of neuroplasticity when it works against us. What happens in many cases is that the neural circuits responsible for processing pain have been activated so frequently and so intensely that they have become sensitized. The connections have strengthened. The volume has been turned up. The brain has learned pain, the same way it learns a language or a musical instrument, through the relentless repetition of a signal until the circuit becomes self-sustaining. The pain is real. It is not imagined. But it is being generated not by the body alone, but by a brain that has rewired itself around the experience of suffering. Understanding this is important, not because it diminishes the pain, but because it offers a path forward. If the circuits were strengthened through plasticity, they can also be weakened through plasticity, through new experiences, new associations, new patterns of input that slowly, patiently retrain the brain to quiet the alarm that no longer needs to sound. Mirror therapy, which uses visual feedback to trick the brain, has helped some patients reduce phantom limb pain by promoting cortical reorganization. This ingenious therapy was developed by neuroscientist V.S. Ramachandran, and it is one of the most creative applications of neuroplasticity in clinical medicine. The concept is simple. A patient who has lost a limb and who experiences phantom pain in that missing limb places their remaining limb in front of a mirror, positioned so that the reflection of the intact limb appears where the missing one would be. When the patient moves their real limb, the reflection creates the vivid illusion that the phantom limb is also moving. And remarkably, for many patients, this visual feedback reduces or even eliminates the phantom pain. The brain, receiving a clear visual signal that the missing limb is present, intact, and moving freely, begins to update its internal model. The cortical reorganization that gave rise to the phantom sensation is gently reversed. The alarm quiets. The pain eases. It is the brain being shown a new truth, or at least a compelling illusion, and choosing to reorganize itself around it. Ramachandran described it as the first example of a successful amputation of a phantom limb. The limb was never there, but the brain's belief in its pain was real. And a mirror, of all things, a simple pane of glass, was enough to change the brain's mind. Focused attention is one of the most powerful drivers of neuroplasticity. The brain changes most in response to what we pay close attention to. Of all the forces that shape the brain, attention may be the most important. Not effort, not talent, not luck. Attention. When you pay attention to something, truly attend to it with your full awareness directed at the experience, the brain treats it as important. It releases neuromodulators like acetylcholine and dopamine that prime the synapses for change. It amplifies the signals being received. It tells the machinery of plasticity this matters. Change here, build here, strengthen here. And when attention wanders, when you go through the motions without truly focusing, the brain does not change as readily. The same activity performed with attention and without it produces different neural outcomes. This is why mindless repetition is less effective than mindful practice. This is why being present, truly, deeply present, is not just a spiritual ideal but a biological imperative. The brain follows your attention the way a sunflower follows the sun. Where you look, it grows. Where you focus, it builds. The quality of your attention is, in the most literal sense, the quality of the mind you are constructing. And right now, in this quiet moment, wherever your attention rests, on these words, on your breath, on the soft weight of your body against the bed, that is where your brain is gently, silently, faithfully at work. Positive emotional states can enhance learning and neuroplasticity, in part by promoting the release of dopamine and other neuromodulators. Joy is not a distraction from learning, it is a catalyst for it. When you experience positive emotions, curiosity, excitement, satisfaction, delight, the brain releases a cascade of chemicals that enhance its own capacity for change. Dopamine, in particular, plays a central role. It is released when something feels rewarding, when a prediction is confirmed, when a surprise turns out to be pleasant. And dopamine does more than make you feel good. It directly supports the molecular processes of synaptic plasticity, making it easier for connections to strengthen, for memories to form, for new patterns to take hold. This is why children learn so rapidly when they are playing. Not because play is trivial, but because play is joyful, and joy creates the chemical conditions for optimal plasticity. It is why learning something you are genuinely interested in feels effortless compared to learning something you are forced to endure. The brain is not indifferent to your emotional state. It is profoundly shaped by it. Positive emotions open the door to change. They tell the brain that the world is safe, that exploration is welcome, that now is a good time to grow. And the brain, ever responsive, ever adaptive, walks through the door. Repeated negative thought patterns can strengthen the neural circuits that support anxiety and rumination, an example of neuroplasticity working in an unhelpful direction. Neuroplasticity is not always kind. It does not discriminate between helpful patterns and harmful ones. It simply strengthens whatever pathways are used most frequently, regardless of whether those pathways lead to peace or to suffering. And this is the shadow side of the brain's extraordinary adaptability. When a person falls into a pattern of anxious thinking, when they rehearse worst-case scenarios over and over, when they replay painful memories without resolution, when the same worried thoughts loop through the mind like a song that will not stop, the neural circuits that carry those thoughts grow stronger, the pathways deepen, the pattern becomes more automatic, harder to interrupt, more likely to fire on its own. The brain has learned anxiety the same way it learns anything else, through repetition. And the more the pattern is repeated, the more firmly it is wired into the architecture of the mind. This is not a reason for despair. It is a reason for awareness. Because the same principle that allows unhelpful patterns to take hold also allows new, healthier patterns to take their place. The brain can be guided. It can be redirected. It can learn something new. But it begins with noticing, with seeing the pattern gently, without judgment, and choosing one thought at a time to walk a different path. Gratitude practices have been associated with changes in brain activity in regions linked to empathy and emotional regulation. There is something almost alchemical about gratitude, the way it can transform the texture of a moment without changing any of the external circumstances. And science is beginning to understand why. Studies using brain imaging have found that when people practice gratitude, when they deliberately focus on what they are thankful for, write it down, or express it to others, activity increases in the medial prefrontal cortex and the anterior cingulate cortex, regions associated with moral cognition, empathy, and the regulation of emotions. Regular gratitude practice has also been linked to changes in the hypothalamus, which influences sleep, stress, and metabolism. The brain, it seems, responds to gratitude the way the earth responds to sunlight, slowly, steadily, with a quiet unfolding that touches everything. And when the practice is repeated, when gratitude becomes not just an occasional thought, but a regular habit, the neural pathways that support it grow stronger. The brain becomes better at noticing what is good, at savoring what is present, at orienting itself toward warmth rather than worry. It is a small practice, a gentle one, but the circuits it builds are anything but small. The concept of a growth mindset, the belief that abilities can be developed, aligns with the principles of neuroplasticity and has been linked to greater academic resilience. The term growth mindset was coined by psychologist Carol Dweck, and it describes a simple but transformative belief that intelligence and ability are not fixed traits but qualities that can be developed through effort, practice, and learning. This stands in contrast to a fixed mindset, which holds that talent is innate and unchangeable. Research has shown that students who hold a growth mindset tend to embrace challenges, persist through difficulty, and recover more readily from failure. And the neuroscience of plasticity tells us why. The growth mindset is not just a psychological attitude, it is a biological truth. The brain can change, skills can be developed, new neural pathways can be built at any age. When a person believes this, when they internalize the knowledge that effort leads to growth, they are more likely to engage in the very behaviors that drive neuroplastic change. They practice more, they persist longer, they pay closer attention, and the brain, following the lead of the belief, delivers on the promise. It changes. It grows. It becomes what the person believed it could become, not through magic, but through the ancient, reliable, deeply hopeful machinery of plasticity. Social connection and meaningful relationships support brain health and may promote neuroplastic processes through emotional engagement and cognitive stimulation. Humans are social creatures, wired at the deepest level of our neurobiology for connection, and this wiring is not incidental to brain health, it is central to it. Meaningful social relationships provide the brain with some of the richest and most complex stimulation it can receive. A conversation with a friend requires the brain to process language, interpret tone of voice, read facial expressions, predict what the other person is thinking, regulate emotions, and formulate responses, all in real time, all simultaneously. It is one of the most cognitively demanding tasks the brain performs, and it engages networks across nearly every region of the cortex. This stimulation supports neuroplasticity. It keeps circuits active, it keeps the brain engaged, and the emotional dimension of social connection adds another layer. The warmth of a close relationship triggers the release of oxytocin, reduces cortisol, and creates the chemical conditions under which plasticity thrives. Loneliness, by contrast, has been linked to cognitive decline, reduced hippocampal volume, and impaired neural flexibility. The brain needs people, not just for comfort, not just for companionship, but for the stimulation, the challenge, the emotional nourishment that human connection provides. You are not meant to do this alone, and your brain is quietly, biologically built for the company of others. Every experience, thought, and sensation you have is subtly reshaping your neural landscape, whether you are aware of it or not. This is the truth that holds all the others inside it, the quiet, constant, all-encompassing reality of a brain that never stops changing. Every moment of your life is leaving a trace. The conversation you had this morning, the song you heard on the way home, the feeling of sunlight on your face as you stood near a window, the worry that flickered through your mind and then passed, the gentle weight of someone's hand on your shoulder. All of it, every sensation, every thought, every flicker of emotion, is touching the brain's living tissue and leaving something behind. Not a memory, necessarily. Not always something you could name or recall, but a trace, a shift, a slight alteration in the strength of a connection, the sensitivity of a receptor, the readiness of a circuit to fire. You are being shaped by your life in the most literal and most intimate way imaginable. The brain is not separate from your experience. It is the record of it, the living, breathing, ever-changing record of everything you have ever been and everything you are becoming. And that record is never finished. It is being written right now, in this moment, with these words, with this breath. The fact that you are listening to these words right now means your brain is already changing, forming new connections, strengthening old ones, proof that you are never truly still, even in rest. And so we arrive at the last truth of the evening. And it is, perhaps, the most personal one, because it is not about a study or a scientist or a discovery made in a laboratory far away. It is about you, right here, right now. In this very moment, as these words settle into the soft landscape of your mind, your brain is at work. Neurons are firing. Synapses are adjusting. Connections that carried these ideas are being tested, evaluated, and if the brain decides they are worth keeping, gently strengthened. You did not have to ask for this. You did not have to try. Your brain is doing it because that is what it does. It responds to experience the way the sea responds to the moon, constantly, faithfully, without effort or instruction. And the experience you are having right now, this quiet, this stillness, this gentle act of listening, is part of the shaping, part of the becoming. You are not the same person you were when this recording began. You are slightly, subtly, beautifully different. And you will be different again tomorrow, and the day after that, and every day for the rest of your life. Because the brain never stops, because you never stop, because the most extraordinary thing about being alive is that you are always, always, always becoming. And now, as we come to the end of our journey, let the facts settle like leaves drifting to the floor of a quiet forest. You do not need to hold on to any of them. You do not need to remember the numbers or the names or the mechanisms. Your brain has already taken what it needs. It has already begun the work of sorting, of sifting, of weaving what mattered most into the fabric of your mind. That is what it does. That is what it has always done. And it will continue to do it long after these words have faded, long after this night has passed, long after you have forgotten the sound of this voice. Because you are not a finished thing. You are not a completed work. You are a living, breathing, endlessly adaptable being, carrying inside your skull the most extraordinary object in the known universe, an organ that rewrites itself every single day in response to the life you choose to live. And so tonight, as you drift towards sleep, carry this one last thought with you, like a lantern held against the dark. You are changing. You are growing. You are becoming. Even now. Even here. Even in the softest, quietest, most restful moment of your day, the brain that holds you is reaching toward tomorrow. And tomorrow, it will be ready for you. It always is. Good night. Sleep well. And know that while you rest, the most remarkable thing in the universe is quietly, gently, faithfully taking care of you.